Hello everyone. Today we are going to learn the partial derivatives of functions of two or more variables. In the study of function of one variable, we introduced the definition of derivative for the function of one variable. Say z equals fx. Its derivative at point x0 is defined as the following limit, where the denominator is the increment of the independent variable, and the numerator is the increment of dependent variable. This derivative reflects the rate of change with respect to x at the point x0. According to the definition, we can compute the derivative of fx by 3 steps. Step 1. Find the increment delta z equals fx plus delta x minus fx. Step 2. Find the ratio delta z over delta x. Step 3. Find limits of delta z over delta x as delta x converges to 0. For multivariate function, we also need to discuss its rates of change. But there is more than one independent variables, and the relationship between dependent and independent variables is much more complex. We firstly consider the rate of change with respect to an independent variable. Suppose f is a function of two variables x and y. If y is held constant, that is, y is regarded as a constant, say y equals y0, then fxy0 is a function of the single variable x. Its derivative at x0 is called the partial derivative of fxy with respect to x at x0, y0. Then we have the following definition. Definition: that fxy is defined in some neighborhood of the points x0, y0. If y is fixed as y0 and x has the increment delta x, then z equals fxy has the corresponding partial increments. Delta xz equals fx0 plus delta x y0 minus fx0 y0. If this limit exists, then it is called the partial derivative of fxy with respect to x at the point x0, y0, denoted by the following notations. We can read this notation simply as partial z, partial x. If z has the partial derivative with respect to x at any point xy of the domain D, then denote the partial derivative with respect to x by these notations. Note, the result is still a function of two variables x and y. Similarly, the partial derivative of fxy with respect to y at the point x0, y0 is given by this limit and denoted by the notations. Similarly, we can define the partial derivative of the function with respect to y and denote it by the following notations. Obviously, the partial derivative of f with respect to y is also a function of xy. According to the definition, the partial derivative can be regarded as the derivative of a single variable function with other variables fixed. Therefore, we don't need new calculating methods. When calculating the partial derivative with respect to an independent variable, we only need to take the other variables as constants and calculate the derivative with respect to the independent variable, such as find f(x), xy. We only need to put y as a constant, then make use of the derivative method of the function of one variable with x changeable. Example 1. Find the partial derivative with respect to x, where f(xy) equals this expression. We take y as a constant, and the derivative partial of f(x) is ey plus 3 times x squared times y. Example 2. If z equals the y power of x, find two partial derivatives of z with respect to x and y. Taking y as constant, the function is regarded as a power function. So, the partial derivative of z with respect to y is y times the y minus 1 power of x. Similarly, taking x as constant, the function is regarded as an exponential function. So, the partial derivative is the y power of x times ln x. Tips: when finding the partial derivative of one variable, treat the other variables as constants. Example 3. The volume of a certain ideal gas is related to its temperature T and its pressure P by the gas law PV equals RT. Where R is a constant, prove the product of the three partial derivatives is -1. From the gas law equation, we obtain P equals RT over V. In order to calculate partial P, partial V, note that R is a constant and regard T as another constant. We can find the partial derivative of P with respect to V is minus RT over V squared. Similarly, we can calculate the other two partial derivatives respectively. One is R over P. The other is V over R. So, the product is minus RT over V squared times R over P times V over R equals minus RT over PV. Note that PV equals RT, so the product is -1. Note, the result shows that the sign of the partial derivative is just a whole notation, not the quotient of the numerator and the denominator. Now we see example 4. If f(x,y) is the following piecewise function, find its partial derivatives. 1. When xy is not equal to 0, 0, by the derivation rules for compound function and the quotient of functions, we obtain the partial derivative of f with respect to x equals the partial derivative of numerator y times denominator minus numerator xy times the partial derivative of denominator 2x over square of denominator. By simplifying, we obtain the partial derivative is this expression. Similarly, we can calculate the partial derivative with respect to y as follows. When xy is equal to 0, 0, by the definition of partial derivative, we obtain partial derivative of f with respect to x at 0, 0 equals the limit f 0 plus delta x 0 minus f0, 0 over delta x as delta x converges to 0. That is the limit of 0 over delta x. The result is 0. Similarly, the second partial derivative is 0, 2. Note, this function has two partial derivatives, but it is not continuous at the point 0, 0. We will prove the continuity in the next section. The definition of partial derivatives can be expanded to the functions of 3 or more variables. Suppose u is a function of 3 variables x, y, and z. How to define the partial derivatives? Similarly, the partial derivative of u with respect to x is the limit of this term. F x plus delta x yz minus fxyz over delta x as delta x converges to 0. Please write down the other two partial derivatives by yourselves. Note, when finding the partial derivative of one variable, treat the other variables as constants. Example, find the 3 partial derivatives of fxyz. To get the partial derivative of f about x, take y and z as constants. Find the derivative about x. We obtain that the partial derivative is y plus 3z. To get the partial derivative of f about y, take x and z as constants. Find the derivative about y. The result is x plus 2 times z. Similarly, the partial derivative of f with respect to z is 2y plus 3x. Example 6. If fxyz has the expression, find the 3 partial derivatives at 1, 0, 2. In order to find the partial derivative with respect to x at points 1, 0, 2, we fix y at 0, z at 2 respectively. Then f is regarded as a function of one variable x. Fx02 equals sine log x squared, and its derivative is 2 over x times cosine log x squared. At point 1, its derivative is 2. So the partial derivative of fxy with respect to x at the point 1, 0, 2 is 2. Similarly, we can find the other two partial derivatives with respect to y and z respectively. This is an easy method. Any other method? In fact, in order to find fx102, we can calculate the partial derivative of f with respect to x firstly, then put the coordinates 1, 0, 2 in the partial derivative. Next, we are going to study the higher partial derivatives. Suppose that fxy has two partial derivatives, fx and fy. Generally, they still a function of two variables x and y. What are the partial derivatives of fx and fy? If both of them have partial derivatives, we call them the second-order partial derivatives of fxy. The four second-order partial derivatives of fxy are as follows. The first expression means the second partial derivative of f differentiating f partially twice with respect to x. The second expression means the second partial derivative of f differentiating f partially twice with respect to y. And the third expression means the second partial derivative of f differentiating f partially first with respect to x and then with respect to y. And the fourth expression has a similar meaning. Partial derivatives of the third and higher orders are defined analogously, and the notations for them is similar. For example, the third partial derivative of f differentiating f partially, first with respect to x and twice with respect to y, will be indicated by the following notations. Here is a question: how many third-order partial derivatives for bivariate function fxy? The partial derivatives of second order and above are called higher order partial derivatives. Example 7. Find the four second order partial derivatives of fxy. We first find the partial derivatives with respect to x and y. By the derivation rules, fixing y as constant, we obtain fx is this term, and fixing x as constant, we obtain fy is the expression. And then differentiate fx with respect to x again, we obtain the second order partial derivative fxx equals 1 over y squared times sine x over y plus 6xy squared. Similarly, differentiate fy with respect to y again, we obtain the second-order partial derivative fyy as follows. Differentiate fx with respect to y, we obtain the mixed second-order partial derivative fxy equals this equation. Similarly, differentiate fy with respect to x, we obtain this second-order partial derivative. We call fxy and fyx as the mixed partial derivatives. Example 8. If z is this function, prove it satisfying the equation, the sum of two second-order partial derivatives zxx and zyy is 0. Proof. Simplify z. Z equals 1 over 2 times ln x squared plus y squared. So the partial derivative of z with respect to x is x over the sum of x squared and y squared. And then differentiating partial z, partial x with respect to x again, we obtain the second partial derivative of z with respect to x twice is this expression, simplifying as y squared minus x squared over the sum of x squared and y squared all squared. By the symmetry of xy, just exchange xy in this term, we obtain the following second partial derivative of z with respect to y twice. Note that there is only a minor sign difference between these two second partial derivatives, so their sum is 0. At the last time, we give the geometry interpretation of the partial derivatives for bivariate function fxy. In order to understand the geometry meaning of a partial derivative, we first review that of derivative for function fx of one variable. See the left figure. The derivative f prime x0 is the slope of the curve fx at the point M. Consider the surface whose equation is z equals fxy. This is the surface of this function. Fixing y equals y0 means that the plane intersects this surface in the plane curve RPQ. Note that fx x0 y0 equals the derivative of fx y0 at point x0. So the value of fx x0 y0 is the slope of the tangent line tx to this curve at p x0 y0 f x0 y0. Similarly, fy x0 y0 is the slope of this tangent line ty. Today, we reviewed the definition of derivative for function of one variable, and then studied the partial derivatives and higher order partial derivatives for multivariate functions. At last, we give a geometry interpretation of partial derivative for bivariate function. Thank you. See you next time.